All right, so we're going to look at an applications of integration question. And this question is quite short, so the shorter the question is, the more worried you need to be, I reckon. All right, so a long trough with a parabolic cross section is 1.5 meters wide at the top and 2 meters deep. Find the depth of water when the trough is half full. Okay, you can see here I've got a parabolic trough that the question is sort of asking about. And we know that at the top it has to have a width of 1.5 meters. Okay, so that means, you could start to think this would be at positive 3/4 and this is at negative 3/4. That would give a total width of the top of the trough of being 1.5. And then this point here is at -2 because it's 2 meters deep. Okay, so what we can do to begin with is think about what the equation of this function is. Given that information that this is at -3/4, positive 3/4, and at -2, I've kind of given the game away a little bit, but I reckon hopefully you'd be able to find what that function is. This is what it would turn out to be. It'd be 32 on 9 x squared minus 2. Now, there's no reason necessarily that I've centered it on the y-axis. I could have moved it anywhere along my Cartesian plane. But let's just keep it simple and put it on the y-axis. Okay. What we would like to do is to firstly find out this cross-sectional area here. So if we found this cross-sectional area, hopefully you would agree with me that it would be the integral from 0 to 3/4, so 0 to 3/4 of the function. And then we're going to multiply it all by 2 because we just find this area, and then to double it, it would also, add on that area because it's symmetrical, right? But obviously we can't have negative areas. We can only have positive areas. So what we could say from this is that the cross-sectional area is 2 meters squared. Now, obviously I've sort of used a calculator there to sort of work that out. But yeah, what we get is a situation where the cross-sectional area here is 2 meters squared. Okay. A key insight in this question is that we're actually talking about volume, right? It says find the depth of water when the trough is half full. Well, to be half full, we're talking about the volume being half full, right? So I suppose what we could say is that the volume is going to be equal to the cross-sectional area multiplied by some length dimension. So to bring things into volume, you need to take an area multiplied by some other length dimension. So we're going to take the cross-sectional area, which is 2 meters squared, and multiply by some length dimension, which is L, which would also be in meters, or which would be in meters. Okay, but then the question says, find the depth of water when the trough is half full. So half of the volume would be half of the cross-sectional area. I think you would agree with that. If we wanted to halve the volume, if we just halved the cross-sectional area and then multiplied by the same length, then we would get half the volume. So that's sort of what we're setting up, okay? So now the question becomes, how can we set up an integral such that we have a cross-sectional area of 1. Okay, because we need this cross-sectional area to be 1. And this is what we're going to come up with. And this looks a bit messy, but let's just take an aside over here and have a think. If we've got some point A that is along here, that's if I put the A value at some point, there's going to give us a cross-sectional area equal to 1. Right? So there's some value of A that's going to give us a cross-sectional area equal to 1. When A is up here at 3/4, the cross-sectional area is 2. So it's somewhere below that, right? So it's somewhere below that. And so what we can do is set up the integral. But now the integral we're setting up is an integral between curves because we need the area underneath this sort of the top of the water level and the bottom of the trough. So what we need to think about is what is the equation of the top of this line, top of the water level? Well, hopefully you'd agree with me that it's just the function evaluated at some point A. So the y value of this line is just 32 on 9 a squared minus 2, which we just get by substituting A into the function. Okay, so now we can hopefully make some sense of this integral. We're taking the integral from some point 0 to some point A along here of the upper function, which is 32 on 9 a squared minus 2, minus the lower function, which is 32 on 9 x squared minus 2. And we need all of that to equal 1. And then remember, we're doing it as a symmetry problem. So 0 to some point A, but then we double it to make sure that the cross-sectional area is a total of 1. So we're doubling it because of the symmetry. Okay, and then this is where you need to get your calculator out. So if we clear all that, we need to first define our function. So we probably could have done that a bit sooner on, a bit earlier on. So if we do 32 on 9, x squared minus 2, highlight that, define that as f of x. Okay, now we need to compute this monster and find out what a is. So hopefully you'll realize that this part here is just f of a. It's the function evaluated at a minus the function evaluated at x. We need to highlight all of that. We need to go calculation, integral, definite integral, the integral from 0 to some point a. Okay, and we press OK, and it's going to give us some answer. Just ignore that. Bring that down there. Don't forget to multiply by 2. Okay, now we highlight all this. Interactive, advanced, solve. And we press, we're trying solving for the variable a now. So we press that and we get the wrong answer. I deleted all my variables. I don't see why that didn't work, and it still doesn't work. Okay, you probably saw a word I stuffed up. It needs to equal 1, right? It can't solve anything if it doesn't equal anything. And a wrong argument type. Of course it is. Okay, let's delete that. You got to be so careful. Calculator has no idea what you want to do. Let's take this again. Let's bring that down. Let's set it equal to 1. Now we highlight it. Interactive calculation. Solving that for a. No, we're not. That's not what I want to do. I want to go interactive advanced solve. Solve for the variable a. Okay, we get an answer, which is 0.5952. We put it in a standard answer, we get this. So that's the value of a we're interested in, is approximately 0.595. So if we come back here, lo and behold, here's one I prepared earlier. We get this answer here. So hopefully you can see that that matches, yeah, with what we had here, right? Okay, it's approximately 0.590. Okay. So we can set our a value to that, 0.59, so that's around there. Okay. Now, all we need to do is, we need to evaluate this point. We need to know where this is now. We know what a is. So we take our function, substitute in a, which is 3 on 4 times 2 to the 1/3, which is this down here. And that gives us whatever this is. So let me show you that on the calculator. So that's going to give us, if we type in f of a, copy that, paste that there, it gives us this 2 divided by 4 to the 1/3 minus 2. Okay, as a decimal, because we sort of need to make some sense of this, approximately negative 0.74. That should make a bit of sense. This point firstly, it's below the x-axis, so it's negative, and it seems negative 0.74 seems about right. Okay, so now we're almost there. We know that the total depth from the x-axis to the bottom is 2 meters. So we need to take 2 minus 0.74 essentially, or another way to think about it is 2 plus this whole thing negated, right? You make this whole thing negative, and then you add that, and then you do 2 plus that, because you're adding on something negative, right? So the exact values can make it a bit confusing, but essentially you're just saying this total depth is 2 meters. This first part is negative 0.74. So this depth here, which is what the question is asking, what is the depth of the trough, is 1.26 meters. Okay, hopefully that clarified that question. I thought that was quite tricky. Yeah, good luck with your studies.